Good afternoon. In our
Good
last
afternoon.
lecture, in our last lecture, we had listened to a very interesting topic, that is troubles in troubleshooting. We now have two lectures in continuation on green sand. I welcome you all in the first lecture today from Mr. Subramanian, who is working in foundry and related areas for about 50 years now, initially with Tata Motors and then as an independent consultant. Apart from providing consultancy in the areas of process quality, troubleshooting, and value engineering, he is also actively involved in conducting training programs and seminars for target groups and writing technical books and educational material. These are some of the material Mr. Subramaniam has authored for NCTS. There are two DVDs, A Journey Through Cold Box Process, Inoculation of Cast Iron Science and Practices, and a book named Green Sand Practices for Defect-Free Castings. NCTS has also come out with information sheets on molding and core sands. To take benefit of these DVDs, books, and information sheets, you can contact NCTS at this email and website. I now request Mr. Subramaniam to address us on today's topic, a workhorse called green sand. Over to you, sir.
Thank you, Savani. Thank you, Savani. And undoubted, I thank IIF NCTS for organizing this short seminar on green sand. We call it workhorse. So the green sand is somewhere in the background, but it is doing a lot of work. So this is our intention to bring out what green sand is going to do for us or has been doing for us. To start with, let me pay tribute to my guru, A.R. Krishnamurti, who is a living legend, who has devoted his life for foundry sand. He is past 90 and is still getting interested in doing some research work in sand. This presentation is the first of two parts that deal with green sand preparation and application in cast iron foundries. So here is an attempt to take you through the path taken by system sand in its numerous cycles while in circulation, to empathize with its travails in transit. We call it travails. We'll see how it is going to be troubled all the way. Okay. So when you think of making castings, what comes to our mind is these three things: the green sand, which makes the molds, and then you pour the metal in the mold. So, and we spend a lot of time discussing the molds, how many number of molds we made, and the metal which will make those castings. So how many castings will be made from those molds? But we leave out the sand. Yes, we leave out the sand. Very sad that we are not talking about sand most of the time when we talk about molds and the castings that we make out of the molds. Well, the sand, a good sand makes a good impression on the customer. So obviously we have to make a good sand. So the beach sand is always beautiful and lovely to feel. But when it comes to the foundry, what happens? Sand gets proper attention only when casting supplies are affected for sand related issues. Isn't that sad? Rest of the time, sand is treated like a pariah. Green sand is pariah, an outcast. We often speak of molds, molds, and molds, but not sand. Let us see some conversations. For most of us, the molds until box closing is important. Conditioning the sand is not a priority at all. Enough if happenings in the sand circulating system is displayed attractively on the panel inside a comfortable AC room. Mixer malfunction or cooler breakdown are just routine issues. Anyway, the sand gets mixed before reaching the molding machine. Why should I bother about these malfunctions? Lab report from sand is nonsense. Anyway, castings are getting sand defects. Only sand parameter of utmost relevance is compactability. Compactability is a God-given word for us. Pourable molds count in production, casting rejects are not my issues. So this is how arguments keep running in the background. Honestly, how many of us would like to make at least one visit along the path of system sand, starting from molding machine through all the processes on the way and return to molding again? If the sand can travel miles and miles in circulation, always at your service, why can't we do it? At least a lap of 1 mile. So let's experience a drone view with a virtual tour of the sand route. So this is the aim of this presentation. So let's look at the drone view to start with, how the lifeline runs in the sand. Here you see the familiar cycle inside the foundry. You have the molds ready for pouring. So you pour the molds and then the castings come out by shaking out the molds. And when the castings are taken out, the sand is taken to the sand cooling area where it is cooled down. And then you prepare it again for the molding purpose. And then you make the mold, set the cores inside, and then close it again. So the whole cycle, it represents the path the system sand travels. Now in this, you will notice the blue zone, which is an ambient zone, and the red zone, which is a hot zone. Hot zone is where you pour the molds, shaken out, and then goes up to the sand pool. Rest of it is the travel in an ambient condition. So this is a hot zone. Now, in the hot zone, a lot of things happen. And in the ambient zone, we repair the whole sand system back to its green state and then get ready for the next pouring operation. So the ambient zone is always a very comfortable, pleasant place, whereas the hot zone is no for me. Pouring and shakeout are hot, humid, and polluting, and one would like to stay away from them. And this is the general scenario inside a foundry. And look at the cycle once again. We can draw a different line here and then say the sand is cooled to make a good mold, and then the mold is destroyed while making a good casting. So this word destroyed is the area in which we will concentrate today. A good mold should produce dimensionally accurate casting, devoid of defects. So that is a fact. So once it has produced a good casting, the mold gets destroyed. So we start our journey from the time the mold is poured and the casting is cooled sufficiently for shakeout. That means the casting has come out and then it has shaken out all the hot sand out of it. So that's where we start with the sand, the hot sand. What happens in the hot zone? Heat affects a part of the sand in the mold. Extreme heat extremely and less heat to a lesser extent. You will see inside a mold. The green part is a mold, and this part is a casting. Metal is a casting, and then you put a core inside, and you see that when some metal is filled, hot metal is filled, then there is a zone which is heat affected, extreme heat. And next to it, we have this partially affected green sand. And behind this, a portion of the green sand which is not affected at all. It is much beyond the hot zone. And the core also, some part of the core which is fixed into the mold, the core print, is also not affected, while the core which is surrounded by metal around is a heat affected part. So now we will see that this red zone in the mold and then the white part in the core which is outside, the core which is embedded inside the metal, all of them are going to undergo extreme heat conversion of some of those ingredients inside. A lot of things happen because of the heat. Now, when you shake out the casting out of this mold, then the rest of the sand, whether it is fully heat affected or partly affected or not affected, all of them are going to get mixed up. The whole mold box without the casting is going to go through the grill during shakeout, and then at the bottom of the grill, you collect all of it on belt conveyors. The sand is extremely hot, humid area, a lot of steam is coming out, a lot of fumes come out, a lot of dust is generated, and one would not like to go near it at all. But this is the area in which you will see a lot of things happening. We'll talk about those aspects a short while from now. What gets affected is the coating on the sand grain. The sand itself is safe because it is a refractory material. Coating becomes fully burnt out in grains closest to the casting profile, while the coating exists in various degrees of deterioration in the grains away from the cast surface. Repeated exposure to heat can alter the structure of the sand grains. We will touch upon this also because sand cannot be used indefinitely. There is some deterioration of the sand also. So now we'll talk about the heat and its exposure. The return sun, which is hot. How much it will get affected is based on the intensity of the heat that is given to the sand and how long it is getting affected and how much it is going to get deteriorated over a period of time. This is all before it gets cooled. So that means everything is happening when it is hot. So obviously, if you can reduce the time duration for this exposure to heat, the sand is going to remain much better than leaving it hot overnight or not bothering to cool it at all. It's like this. When you can get scorched under the sun, the sand is also in a similar way getting affected. So as the temperature rises in the return sand, we see a lot of things happening. First is the free moisture. The earliest thing that is going to come out is water that can evaporate quickly. It becomes a steam and then escapes out. And the volatiles which is remaining in the sand, volatile material, we will come to the volatile material little while later, they also burn out or they also volatilize. They will burn out if there is oxygen around, otherwise they will just volatilize. Then there is a combined moisture loss, which we will talk about, and carbons, which are part of the additives. And then some part of the bentonite gets burnt out. What happens when these things happen? The free moisture loss, of course, we can replace the water that has gone out when you are reconditioning the sand. Combined moisture also can be replenished, but the burnt products of carbon like ash or coke, they cannot be they are not useful, they are just contaminants. So they are going to build up inside the sand. The bentonite that is burnt out is called dead clay, which is also a contamination. So now you need to replenish some part of this dead clay with good clay. You need to replenish the ash, coke contents which are coming out of carbons. So you replace the carbons. You can put some more moisture to get it back to its green state. So after the check out, the sand is a mix in various degrees of deterioration. Unless mixed thoroughly, average properties can't be tested. If the mix is not cooled quickly, the losses will increase. So these statements are like this. So you need to cool it quickly, that is one. The second is you should mix it thoroughly before testing it. Ash, coke, burnt clay or fines that simply absorb free water. They are just like blotting paper. They interfere in strength buildup, interfere in permeability of the sand. Higher percentage of fines is a major cause for casting scrap. So look at the returned sand again. So these are the constituents of the returned sand. You have a large part of it is the unburnt system sand. Then you have burnt additives and oolitics. I'll talk about oolitics soon. Then you have some metallic contents, which are part of the casting, which are spillages, fins, vents, and things like that. Then you have poor sand, semi-burnt. The core collapses. Sometimes it remains as lumps, and then you can take it away above the shakeout. Some are crumbling and then falling into the grill. Washers, gaskets, which are part of the molding system. Now, these additives to the system sand have undergone many changes. Additives means these are the additives. Some of them are burnt. They have undergone many changes to combat specific issues related to sand and its applications. That means there are newer types of additives coming in. Some of them could be anti-veining products, wood flour or similar products, substitutes for coal dust, use of petroleum products and residues, lustrous carbon, and similar items which are getting added into the sand. So all these are definitely contaminants for the sand, but for good purposes, for it they are added into. Such items remaining in the sand can substantially alter the quality of green sand from its prime duty to provide green strength. Now, why is it? Because these products are very small in size, much smaller than the sand grains. So when these products are added, they have a surface area which is very high compared to the sand itself. And they are water absorbent, except for perhaps the lustrous carbon. Everything else is going to absorb some moisture. So when you are adding water to the returned sand for reconditioning, some of the water will be absorbed by these and then deprive the actual bentonite from absorbing the water for its strength purposes. So getting ready to face the heat again, which means that you are going to condition this hot sand back to its molding capacity. Let's look at what went wrong due to heat. What happens to the binder? There is a burn loss, which is burnt clay. Then some of it goes as dust while we are extracting the dust at various points in the foundry. Then there is an oxidation loss, like some of the carbons are burnt as carbon monoxide or carbon dioxide. Some carbon will get into a form of coke. Then the volatile materials can volatilize and sometimes produce lustrous carbon also. Then you have water which is lost due to evaporation, and the combined water is the ionic bond which is lost due to extreme heat. The raw sand that is lost in transit, in transfer, in sometimes during suction also. The fine sands are also lost in suction. Then there is a oolitics. Then the last stage is the finishing part of the casting where a lot of sand is stuck to it, and then most of it is ground, and then most of it is dusted, and then shot blasted, and then everything is a waste. You can't recover anything from this part of the sand. So these losses will have to be replenished. This water has to be replenished. These carbons and volatiles have to be replenished. These burnt and extracted losses have to be replenished. So replenishment of lost vitals in the system consists of moisture, the binder, and carbons and hydrocarbons. The return sand for reconditioning has to be analyzed to find out what is deficient and by how much. So such analysis should be done in a thoroughly mixed condition when the sand has attained ambient temperatures fit enough for subsequent mixing cycles. Here, the mixed condition, thoroughly mixed condition is important as well as the ambient temperature. When you can't take out a return sand which is very hot and then check it, because by the time you bring it to the lab, some moisture will be lost. So you would not know what is the actual moisture content in that sand. Similarly, if you are not mixing it thoroughly, you will not be able to assess what is the remaining part of the binder, remaining part of the coal, remaining part of the sand. You will not be able to assess it. So let's talk about moisture loss. So to add this moisture, or to compensate this loss, you have to add some water. So we add water, and then this addition is not simple arithmetic. So the demand concept is like this. For activating the bentonite, you require water. For compacting the sand, you require water. And both of them together will help in making a rigid mold. So what is bentonite activation? It can be seen in two ways. One is pre-activation, the other one is final activation. And for compaction, there is what is called temper water. Now, what is pre-activation? Pre-activation is before the sand goes into a sand mixer. The sand should retain some water so that your bentonite, which is remaining inside the return sand, is activated to an extent and then reduces the load on the mixer. Otherwise, you will have to add a lot of water inside the mixer and then wait for all of the water to get absorbed. This activation of bentonite is not instantaneous, it takes some time. So always pre-activation is going to help in activating the bentonite before it reaches the mixer. And the final activation can be done inside the mixer during the mixing cycle. So the return sand should have retained moisture. This is pre-activation, about 1.8 to 2.2%. This moisture keeps the bentonite pre-activated, while further additions of water provides for full activation and also for the desired compactability levels in mold. It is a temper water. So here the word compactability is introduced. Now, how do you cool the sand? Water is the best medium for fast and effective cooling. There are various ways of cooling. One is using water, which we are going to discuss. There is a drum which is rotating, and then you can use air, and then the whole thing is rotated, and then there is a tumbling action, then there is a suction. Inside that you can have water sprayed also. This method is to use water because water, when it added, it is going to form steam, and that steam is going to take away some heat from the sand. So we talk about the features of the sand cooler. It has got three aspects. One is the blower with control suction. Then there is a provision for water spray, and inside the mixer there is a plow and then plow for plowing and then shifting. There are no beaters inside, but these are the basic features that are required. And what are the functions of the cooler? One is vapor desaturation, because when you add water, there's going to be a lot of steam. And inside the cooler, if you have supersaturation of water, then there is not going to be any removal of moisture from the sand. So you need to take away the heat. To take away the heat, you have to take away the steam from the upper space in the cooler. So you have to desaturate it. How do you desaturate? You have to keep on sucking out the hot air from inside. And also you have to blow air from the bottom to keep the sand moving about and expose it to as much of the water as possible. Quenching is the medium, water is the medium for quenching, and then blending is a plowing, etc. What are the parameters for control? One is moisture. Moisture is controlled through two probes, one in the entry and one at the exit. The humidity levels are maintained. And then the temperature is controlled, input temperature and output temperature. Then homogeneity is maintained by the cycle time. How long it remains in the during mixing is going to decide how much is the homogeneity inside the sand. So let's talk about how much to cool the sand. Let's say how cool should be cool. Entry of return sand to the mixer should be at ambient temperature. That's our aim. So it was very hot. The temperature of the metal was 1400 plus. And the sand would have reached something like 800, 900 degrees. And from there, by the time it comes to the cooler, it will be still very hot when it is all mixed up with unreacted sand. Then the temperature should be something around 80, 90 degrees. So what is this temperature got to do with making molds? At 38 degrees, when you prepare the sand, all that sand parameters are stable. But when it reaches above 48 degrees, all the parameters become unstable and you require a lot of time to melt the sand. And when it reaches 60 degrees and you make the molds are very friable and very weak. And if the temperature of the sand is 70 degrees, you just cannot melt the sand. As you add the water, it will evaporate. So obviously, this 48, 60, and 70 are not the temperature of the sand when they enter the mixer. The mixer needs a very cool sand, which is very close to ambient. Many foundries suffer from this basic requirement in the sand. If the temperature of the sand is higher, then most of the properties will be lost. For example, we are saying water is getting evaporated. So when the water is getting evaporated, the bentonite which you added, if it doesn't get that water and the water is going to evaporate, the bentonite will not be able to develop the bond that is required to hold the sand grains. The obvious result will be the sand grains are not held together in the mold, and then when the metal is poured, they are going to become loose and then they get included inside the casting. Particularly if we have some ingots which are very close to this weak part, and then the sand is going to get eroded and then it will spoil the casting. And you won't be able to make the mold because by the time the hot sand reaches the molding machine, it has lost its compacting ability. So by compressing it, it's not going to make a good mold. When you remove the pattern from the mold, sand is going to collapse or it is going to get rubbed out. So better to stay between 38 and 42. So this essentially tells why cooling of the sand is very important in the process of reconditioning. Now let us get into the ingredients of the sand mix. The basic binder is bentonite. In chemical terms, it is an absorbent aluminum phyllosilicate clay consisting of montmorillonite. Montmorillonite is a mineral which is existing in this form. It has got exchangeable cations sandwiched between two layers of montmorillonite. So one montmorillonite crystal will have a tetrahedral sheet of silica, an octahedral sheet of silica, and again a tetrahedral sheet of silica. This is the general structure of montmorillonite. So each silica tetrahedron looks like this, and then a cluster of them in one layer. And then you have the aluminum octahedron in the second layer, and the third layer is again the silica. Now, between this and another montmorillonite, you have this exchangeable cations which are hydrated. The NH2O represents the hydration. Looking at it a little more deeply, we see that cation exchange can be done. So this bentonite can be either a sodium based or a calcium based or a magnesium based or a potassium based. So all of them can hydrolyze and then they can occupy this position between two crystals. Now, in the unhydrated situation, it will be like this. And when they hydrate, you can exchange the ions. So if you want to convert a calcium bentonite into a sodium bentonite, you use soda ash and then water. So there will be an exchange of sodium into the calcium space. Now this water also is going to increase the distance between the two crystals. This is called swelling. When the absorption of water takes place, OH molecules occupy some space and then increase the distance between the two crystals. And then you see that this is the expansion that is taking place, swelling, due to the hydrated cations. So this is the test that you do to determine how much swelling capacity a bentonite has got. So this is an incoming test that you can do. After being left for 24 hours, you'll be able to see that swelling has taken place. So swelling denotes the extent to which hydrated bentonite can coat the surfaces of sand grains. What it means, when the bentonite in the powder form is a small volume, and if it is going to increase in volume when the water is mixed with it, then there is a good coverage of the sand grains by this increased volume of bentonite. You know, when you make the mold, it is not the sand that is going to hold together. It's only the binder that is going to hold together. So the binder has to be entirely on the sand, and then it is a binder to binder contact between the two sand grains that is going to determine how the sand grains are going to be held together, and then they are going to make the mold. Now we come to the volatiles and the carbons, which means they are going to determine how good the castings are going to look, how good is the surface finish. These volatiles are supposed to provide a barrier by creating volatiles in between the hot metal that is coming in and the mold. So it's the protective layer it is supposed to work as. So that is the purpose. Initially, the second thing is, it is because they are hydrocarbons, they are supposed to burn by using the oxygen in that mold atmosphere inside. So the oxygen doesn't have time to mix with the iron and then produce oxides or slag, which are again inclusions. So, and second, it is going to give a film. That's what is the general theory. We will see about it again. The surface quality of casting is decided by basically the sand roughness. That means if it is a very coarse sand, then the casting surface will be rough also. The second is how good the compaction is. If the compaction is not good enough, then there will be porosity in the mold. And then the refractoriness of the sand itself. If it is not refractory, if the quality of the sand is poor, that means it is contaminated with a lot of fluxy materials which are going to reduce its refractoriness. Then with the temperature of the metal, it will start fusing and then they can get stuck to the castings. So these are all cases where you will see surface quality is affected. Then we talk about the coatings, the binder and the residues. They also affect the surface quality. The coatings means what you're going to put some coatings on the core, on the mold, and the residue that is coming out of it, and then they get mixed with the sand. Then the surface quality is decided by the oxidation and the physical barriers that it provides while in the pouring stage. We're talking about the sand roughness. You get rough surface because it's the penetration of the metal between the two sand grains. Sand grains roughness is one. Second is if it is not compacted well enough, then you will get a rough surface. If they are compacted well, it might be improved to a smoother surface. And if you are going to use a finer sand instead of a coarser sand, it will be smoother still. Now we talk about the barrier, which is an envelope of volatiles coming out of the volatiles addition with gas blanket theory. The gas blanket theory says if you have the metal like this here and then the mold here, then you get a gas blanket here, which is going to protect the mold from the hot metal. But this concept is not correct because in general, the gas that is going to develop will always have a tendency to move upwards. So when you're pouring a heavier casting, the metal which is first entering the mold will try to settle at the bottom of the mold and then start slowly rising. So with the weight of the metal, the gases don't have a chance to remain there. They won't remain, they will just escape out. So you will always see when you pour a heavier casting, the drag portion of the casting is rough compared to the coke portion. So this gas blanket theory doesn't work always, unless the metal quantity is very less, like exhaust manifold or small castings, where the metal itself is not much, and then there is a quick solidification taking place. In those cases, it might work. But the more important aspect of this volatile is to provide a graphite barrier. Graphite barrier means lustrous carbon is a crystalline carbon which is non-wetting. It is non-wetting to metal. So it prevents metal penetration and also prevents reaction with the sand. It provides a layer. So instead of a gas barrier, we are talking about a graphite barrier. So this is the right explanation, and then we'll see how this actually works. How the lustrous carbon is formed. Here we have the mold cavity. You have got one side of the mold and another side of the mold. This is a cavity space in which the metal is going to flow now. The liquid metal is coming from one side into the mold cavity. It is going further. So it is going. So you will see that there is a black layer coming here. This is lustrous carbon. How this is formed? It is formed by low temperature and reducing atmosphere. What is low temperature? Because the advancing metal is continuously losing temperature. You know this? front of the metal is always colder compared to the remaining part of the liquid. And then the mold here is again cool, which is ahead. The mold here has become already warm. And this mold has become cool. So there is a low temperature zone here. Now, the volatiles in the mold here are going to produce volatile substances, which are gases. And some part of it is going to burn to carbon monoxide or carbon dioxide. And then the area is going to be depleted from oxygen. So it is becoming a reducing atmosphere. So that these two contribute to the production of lustrous carbon, that is precipitation of carbon in the form of crystals, which are very fine flakes. Now you will see that the same reducing atmosphere also produces lustrous carbon on the walls of the mold. So you have got this carbon, because the metal itself is having a high carbon content, 3.3, 3.4%. So this is also going to help in retaining a lustrous carbon layer in front of it. So now this is the theory. This is the barrier that is going to be provided for the advancing metal. And then you have a smooth surface. So what we need is not lustrous carbon inside the mold, inside the sand. We want what is called lustrous carbon former. Lustrous carbon former is the volatile addition that we are going to do. It has to create lustrous carbon while the metal is poured. So it takes away the oxygen to start with. So it has to have a high carbon content. And then it also gives a softening effect. So it cushions the silica from its expansion. Silica, when silica is the sand that you are using, so due to heat, it is going to expand. So to counter this, there has to be something to absorb the expansion forces. So the softening, the lustrous carbon former will have to soften also. And then when it becomes a coke, then coke occupies more volume. So the same lustrous carbon former, it softens and then it expands while becoming a coke. And that coke is going to counteract any shrinkage effect of the bentonite. Shrinkage is because of bentonite is losing the combined water, and then what has swollen during the molding process is going to shrink back to its original state because the loss of moisture in the combined. All the hydroxyl ions are going to become lost. So then that shrinkage cavities or shrinkage space is taken by the expansion of this coke. The only negative aspect of this lustrous carbon is the coking. The coke that is produced because of this expansion is a residue which is porous, and then it is a dead matter. It is going to absorb a lot of water by itself and then rob the bentonite of the water that is needed for development of bond. So adding lustrous carbon to sand mix as a carbonaceous additive does not serve the purpose. So all that you require is a lustrous carbon former, which is in the sand. It can remain in the sand as long as it is not affected by heat. But when the metal is poured, that part of the lustrous carbon which is close to the metal in the mold is going to give all these benefits. Hence the surface finish improves. Now talk about the sand itself. We talked about the binder, we talked about the carbonaceous additives, that is the volatiles. Now the silica itself. The silica itself is going to die. So how it is going to die? These are the final moments of silica grains. We'll have a look at it. When it is new, it might look like this. When it is 3 times recirculated, someone has done this experiment, so I picked up this picture from them. 3 times recirculated, you will see that some layering has formed on top of it. And then when it is circulated 6 times, you have got more and more layers one over the other sitting on the sand grain. So it's not uniform, but it is there in some places, it is there in some places here, some places here. So generally, there is a weakening of the refractoriness over a period of time due to multiple circulation of these sand grains inside the system. You know how this is called woolitization. they become oolitics. The oolitics are again porous. These deposits on the sand grain are very porous and then they absorb water. So that is another negative aspect. But they also provide some cushion to an extent when you can accommodate some amount of this oolite on the sand. They will provide a cushion for expansion of the sand. But beyond a certain level, they become a nuisance by absorbing too much moisture. So during repeated recycling of system sand, the sand grains will be repeatedly coated with bonding clay layers, that is this, which are successively calcined and baked over the sand grains on exposure to thermal forces. Thermal forces are coming from the liquid metal, which is very hot, and at that temperature, this bentonite gets calcined, that is burnt and baked over, that means it sits on the sand itself. Now how they are? They are forming from the sand grain, one layer, second layer, third layer, like that, they build up over and over, and then they become oolitized. So some time we have to do to remove these oolitics and then add fresh sand. Now the problem is these oolitics cannot be seen or cannot be separated in an easy way because they are all mixed up. They don't have too much of density difference where you can employ some differential separation techniques. So it is not possible, and the quantity is so small, but they are significant. So it is not possible to identify and discard all the silica sand grains that are oolitized. So what is done? The practice is to discard a reasonable portion of the returned sand based on sand to metal ratio, which will decide how much of the oolitization is going to take place. And the influx of sand from bonded core burnout. You always use sand cores which get burnt out during the pouring and then cooling process, and then some of the sand gets into the system. So that sand, together with the burnout that is going to take place due to the metal that is going to be resident inside the mold, and taking that into account, you have to replenish the deficit with fresh silica sand and rejuvenate the sand system. So you have to discard a reasonable portion. The reasonable portion will vary from foundry to foundry and the product mix the foundry employs and the type of castings you make. And also how long you are going to keep the castings inside the mold before it is shaken out. Hence, the requirement of binder and other additives will have to be determined on a continuous basis by periodic assessment of the status of the return sand. Let's repeat it. The requirement of binder and additives will have to be determined on a continuous basis by periodic assessment of the status of return sand. So return sand analysis is the crux of the whole process, and that has to be done in a thoroughly mixed condition at ambient temperatures. Now, having done all this, we have to send this sand to the mixer. It's also called the muller. So what is it? What is this mixing? If the sand grains are not coated uniformly with bentonite, strength of the compacted mold will vary in different regions. Performance of carbonaceous additives will also be erratic. How do you understand this? There is a simple example. You have this peanut chicky, which has got only two ingredients. One is the peanut, the other one is the jaggery. Now we can equate the peanut with the sand and the jaggery with the bentonite. And then I'll understand if the peanut has to be made uniformly like this, then you need to mix the jaggery with the peanut thoroughly. If it is not, then part of the chicky is going to collapse. Coating should be adherent on the surfaces and flow under compaction forces to create bond between the grains. So adherent on the surfaces means that is why you require a mulling action. So you require energy to simply push the bentonite onto the sand grains and then make it stick to it. And then when you are compacting it, this bentonite which is resident on each grain will stick to each other under the compaction forces. and then produce the mold. Mulling and intensive mixing provide energy required to overcome stiffness offered by the activated bentonite and homogenize the distribution of all additives. So now the stiffness is developed because of the water entering the non-morelinite spaces. The hydrolyzed cations offer this stiffness. Then the water addition should take care of adequacy for this activation of the bentonite, as well as the free moisture needs which are required for compaction, generally called as compactability. We'll talk about this in detail in our next session. So it is enough to know that there are two types of moisture here. It's a pity sometimes the mixer cycle time is not given the priority it deserves. Often it is adjusted to suit the speed of the molding line. What it means is you have a requirement of molds, and I have a molding machine which can produce something like, say, 40 molds or 60 molds or 100 molds, 200 molds per hour. Then if you are making that rate of molding or mold making, then you require that much sand to make those molds. So the demand for the sand increases. So the general tendency sometimes is to cut short the mixer cycle, adjust it so that it can meet the demands of the molding. So this is a fallacy. So never shorten mixing cycle time in order to satisfy mold production rate. Better to increase mixing capacity. That means mixing capacity, go for a bigger mixer which can deliver more tonnage per cycle. As well as it facilitate sand cooling and storage. The moment you increase the sand output from mixer, then you have to, down the line, all the areas where the sand is getting converted to a cool sand, mixed sand, and bentonite pre-activation inside the silos. All these things will require additional capacity to match the capacity of the mixer itself. So what is the best way? You always should have a buffer inside the sand system so that any change happening inside the molding side, whether sometimes you might increase the hydraulics by putting an additional pump, so you can shorten the cycle time by maybe 10 seconds or 15 seconds, by which you will be able to produce some 10% extra molds. So all these are possibilities in the production. So you have a larger capacity for sand handling, than sand mixing, and sand delivery, then you are better off than cutting short the cycle time and spoiling the sand mix. Now we start explaining the compactability portion of the sand where extra moisture is added. Now this has to be differentiated from another term called compaction. So what is compactability? What is compaction? Compactability is like money stored in a bank account, whereas compaction is like using that money for value creation. So compactability is the ability for compaction. It's a measure of assessment of the sand. Compaction is the process of action to compact and densify to get a mold. Therefore, a sand capable of getting densified to a certain degree can be compacted to that level of density. So clearly it depends on the forces applied during compaction. Hence, directly relates to the capability of the molding machine. If the molding machine is not capable of compacting, what is the use of producing a sand which is got a certain compactability? So a substandard molding device cannot produce dense molds even if the sand is compactable. Similarly, a capable molding machine device or device cannot compact a sand adequately if it lacks the required compactability value. So both are congruent. We take the next step of rejuvenating, that is moisture. So there is a balance of moisture in water addition. See, whenever there is a mold breakage, there is a tendency to increase the compactability. That means a fashion to increase the moisture. It works sometimes, no doubt. But basically the moisture is required for activating the bentonite and produce green strength in the sand. And the second aspect is about compactability. And the third is, as you mix the sand and then produce this compactability, by the time you reach the molding machine, there is going to be evaporation loss. So you add some more water to compensate for this evaporation loss also. So water addition beyond the needs of bentonite to develop the strength is primarily for temper water needed for molding. That is the compactability. And if the sand has absorbent dead fines, we talked about many things, dead clay, ash, coke, etc. Free water will be spent on them, a definite source of defects in the casting due to blowholes. Now, these absorbent dead fines are a deadly sin in the casting, so we need to control that. See, this water, free water, a gram of free water at 100 degrees will convert it into so much cc, 1660 cc of steam. So it offers a tremendous amount of pressure inside the mold. Talking more about the fines here, you will pay a heavy fine if your dead fines build up in the system. So don't allow it to build up. So you need to have a suction, efficient suction system. So you keep monitoring the fines in the system and then accordingly adjust your suction parameters. The various fines and their constituent elements in the fines. What are the active fines? Hydrated bentonite, starch, etc. Active fine. That means a bentonite which is still having some retained moisture. Useful fines, dehydrated bentonite. That means combined moisture is lost here, and then the hydrocarbon wood flour which are still active. Useful part of it, coal dust are the substitutes which we added in the sand, which are these are coming from the unburnt portion of the mold. Dead fines are close to the sand close to the metal surface. And then the silica fines, which is part of the silica sand system itself. And also some part coming from the coatings, mold and core coatings, which are having silica fine dust. Now this silica fine dust is also having a lot of surface area, and then it demands bentonite, and that bentonite demands water. So we have to control all these fines so that your excess moisture is taken care. How do you remove the fines? Dust collectors support useful as well as useless fines. So the proportion will vary at different suction points in the path of return side. So that has to be done by careful analysis of the sucked out fines, how much of the fines are active, how much of the fines are inactive at various places. And accordingly, you adjust the suction system and then blend them if you require them. The fines are required to improve surface finish because they occupy the spaces between the sand grains, whereas dead fines release absorbed moisture earlier than active fines. Moisture absorbed by the active bentonite is in a hydrolyzed state, held by ionic forces. So they require more energy to break the bond. If dead fines are in excess, more free moisture will remain in the mold. Release of free moisture in large amounts during pouring, that is 1 gram, we said, 1667 cc of steam, can result in explosions, big and small, inside the mold. So judicious use of reuse of fines can benefit the process. So thus far, the sand became cool, turned about multiple times, got rid of some dead stuff, received some nutrients, and got itself fit to get its name, green sand. So we have traveled this far. We started walking with the hot sand from the shakeout and are now proceeding from the mixer towards the molding machine. We will discuss in our next presentation other duties the green sand performs in the service of creating good castings. Thank you for your patience.
Thank you for making all of us understand the importance of giving attention to sand. I must say, and many attendees will agree that the narration was an eye opener in many ways. The details of sand, binders, volatiles, carbon, all of which we tend to neglect, and some of the myths shattered, provided a different outlook. The concepts of lustrous carbon, compactability were all explained very nicely, sir. Thank you. Thank you for the informative lecture. Thank you, sir. And thank you, everybody.
Thank,
Thank you.
thank you.